Chairman. So the title of this work is Fitting and Uniform Corrosion Effects on Ultimate Strength of a Bulk Carrier. My name is Momčilović, and I'm coming from this building, from the Faculty of Mechanical Engineering, within the Department of Naval Architecture, and I'm one of these 5 co-authors of this paper. So let's begin. Okay, so everything that we see physically around us, almost 90% is carried by ships. Out of that, almost 1/3 of all cargo traveled by the seas and land are carried by specific ship types called bulk carriers. They consist of maybe 35% of the all merchant fleets. They carry basically unpacked cargo, which is grain, coal, iron ore, wheat, cement, steel, sugar, and have a significant influence on the world economies. And here you can see the shape of the one cargo hold, which is structured within this cargo ship that you see on the slide. So this is basically a box shape in which you load and unload the cargoes. When it comes to age split, almost 60% of these ships are aged between 5 and 14 years, and ships are generally designed to last until being 25 years of age. So we can conclude basically that ships have to be designed according to their reliability and longevity to experience service loadings, as well as we call it, once in a lifetime loadings. In that sense, we have basically 2 approaches in structural assessment. The first one is, of course, traditional one, in which we assess the elastic response of the hull, steel hull. Basically, we impose service loadings, and then you obtain stress. You evaluate this stress based on the allowable stress, which is prescribed by the rules. You can use prescribed rule-based formulas that are based on the experience, analytical and numerical methods, and also direct calculations. Most notably, I would mention here buckling assessments, because ships are very prone to buckling and the sudden collapse because they have slender plates, and the slenderness of these plates are very high, maybe compared to some other conventional structures. And basically, the outcome of this assessment is that whether you state that some type of the structural member experience yielding or collapse or failure. On the other hand, we have ultimate strength calculations or assessments that are emergently being used in the past decade. They are based on elastic and plastic response of the hull. They basically evaluate extreme loadings or once in a lifetime loadings, such as some overloading events, significant waves, grounding, or improper overhauling. And here you can see the point from which what happens when you reach the ultimate strength of the complex structure of the hull. The ship basically breaks in 2, and this collapse can be very sudden, basically in a few seconds. And here I prepared a video, but I forgot to copy paste the video along with the presentation, so forgive me. This is a very illustrative video on there. On the left side, you have a bulk carrier barge here near Belgrade on the Danube. This event happened a year ago in May 2022. And on your right side, it's a specially designed ship that is extracting the sand from the riverbed and placing it on this river bulk carrier on your left. And the rate of this load is, I'm just talking about the nature of this collapse. The rate of this loading is very small, but the collapse is sudden. And you have this video online. It's a very famous video, and it basically shows the nature of the collapse that can happen. So in order to avoid this type of things, you can do some kind of ultimate strength analysis. This is basically, you evaluate what is this tipping point from which the ship will collapse. You can do that by employing progressive collapse analysis, that is incremental iterative method that is used over the past decade more recently. Some other traditional ones, for instance, nonlinear finite element method, Pikes-Mansur method, some traditional, for instance, Caldwell method. And the outcome of this assessment is basically that you state what is the point from which you will lose your ship. And of course, by losing your ship, you will produce an environmental disaster. That is very important. Okay, so what we used here is progressive collapse analysis, and basically it relies on a few principles. Firstly, you have the hull cross-section, and here is the deck area, the side area, the bottom area. It is halfly submerged into the water, and what you do is you divide your cross-section into for instance, 100 subsegments. Each of the segments represents, for instance, one stiffener one plate or a beam or stiffener with attached plating, a small structural units for all of which they have their own designated stress strain curves, both in tension and compression to take into account buckling and also post-buckling behavior of each of the structures. So each of these segments has its own curve. It's not just one curve for all segments. Okay. So the next thing that you should do there, you impose an incrementally increasing curvature on the hull. We call this sagging bending, and this is a hogging bending. For instance, let's talk about sagging bending. You try to impose the curvature. By doing that, of course, the sum of axial forces have to be 0, and you have to calculate the instantaneous change of the neutral axis. As you impose the curvature, the bending rises. As the bending rises, these upper elements collapses and lower elements experience yielding. Then you have to calculate the strain of each segment, and finally, the main outcome of this procedure is to produce a bending moment versus cross-section curvature diagram. And when this slope here becomes negative, that means the ship or the vessel has reached the tipping point from which the ship will collapse. Okay, so however, in recent years, we try to incorporate some other phenomena. For instance, aging with respect to corrosion, pitting, and uniform corrosion. So here we model pitting corrosion by means of pitting intensity degree. This is basically the percentage between the pit affected and element area, and corrosion intensity degree. This is basically the depth of these pits. By having these two parameters, you can actually calculate the actual volume loss by these pits, and you can subtract the original thickness by this actual volume loss to obtain this novel thickness of the aged element, particular element of the ship. So when you have that reduced thickness, you have also changed your slenderness ratio. When you change your slenderness ratio, you change the ultimate strength of the particular element. When you change the particular element ultimate strength, you also change the ultimate strength of the hull, complex hull of the ship. And on the other hand, when it comes to uniform corrosion, this phenomenon is much more simple because you just reduce the wastage of uniform wastage of the material. So basically, we updated this method with within the method, we programmed this reduction of the thickness and change of the slenderness ratio of each of the elements. So let's see some results. We plotted here the bending moment versus curvature. So you are basically here increasing the curvature incrementally and calculating the actual bending moment needed for such curvature. And this is the slope or the curve for the new ship. And this is for in case of pitting. For instance, we have several scenarios. For instance, all elements are in pitting, or some of the elements experience pitting. And you can see that this ultimate strength or tipping point from which the ship will collapse are not the one that industry standards are now taking into account. When it comes to aging, these ultimate strengths are significantly lower and can be up to 30% than when we consider the novel ship. When it comes to uniform corrosion, the same is performed here. Let's just see the right side of the diagram because of the time I have here. This is the new ship, and some scenarios in which the ship experienced uniform corrosion, and you can see also the reduction of the ultimate strength is also significant here, up to 15%. And here I have a diagrams. These are just extracted from the previous diagram. It's just extracted the ultimate strength. You have the novel ship. You have the ship with this is the bending moment. Also here, the level of the bending moment, ultimate bending moment for collapse, let's say collapse bending moment with respect to the uniform corrosion of 10%, 25%, and 25% is basically the criteria for industry standard for renewal of the platings. And here is the reduction of the dependency of the reduction of the structural members affected by pitting corrosion. Okay, so to conclude, basically in recent years, these ultimate strength assessments are presenting a paradigm shift in ship design. Ships are of course designed to withstand service loadings, but also we have to take into account extreme events. Recently also, when you couple this with the aging effects, It appears to have significant effect on the ultimate strength of the hull. When everything is within elastic limits with so small, for instance, for Mises stresses, everything appears to be safe. But when you cross the certain limits, these effects, such as, especially for the buckling, these smaller effects are having increased significance. Of course, corrosion is here modeled by reduction of the thickness, reduction of the volume loss, actual change of the slenderness ratio, and change of the particular ultimate strength of the particular stiffeners or platings. And of course, procedure for ship maintenance can be updated based on ultimate strength assessment of aging ships. And something that we for further investigation need as a naval architects, maybe from you guys that are from material science, which we are not from. Maybe we need to update these data from other parameters, such as stress strain, aging of the stress strain curve, of the modulus of elasticity, or yield strength aging. So basically, that would be it about the work. Okay, so we have a good picture of our host Belgrade here. Thank you.